This video will cover section 9.2, Arithmetic Sequences and Partial Sums. The objectives will be to recognize, write, and find the nth term of an arithmetic sequence, also to find the nth partial sums of arithmetic sequences, and also to use arithmetic sequences to model and solve real-life problems. So first, what is an arithmetic sequence? So a sequence whose consecutive terms have a common difference is called an arithmetic sequence. We have here the definition, and as we learned in the previous section, when you have a sequence, the terms are labeled by a little subscript. In this case, we have a sub 1, a sub 2, a sub 3, a sub 4, and so on. Since we do not know the last term of the sequence, you could see the 3 dots at the end. That means it is an infinite sequence. However, there is a term here that is considered the nth term, so nth, such as, we don't know, it could be the 5th, the 6th, the 7th, the 100th, or of course even bigger than that. So we're going to use that a lot, so get familiar with it. So n is going to determine the place on the sequence for that particular term. So we use the letter n to generalize it. Now, what we just went over is an arithmetic sequence when there is a number d such that if you take two consecutive terms, as you can see with a sub 2 and a sub 1, the difference of those two will be equal to d, as you can see there. Now here we have the equal sign repeating, so it's telling us that every single difference there. So for example, if I was to take the third and the second term and subtract them, like you see here, you will get the same number, call it d. And similarly, if you take the fourth and the third term, subtract them to get the difference between them, you will get the same number, and so on. So that number d, it's called the common difference of the arithmetic sequence. And so that is the condition so that your sequence is considered to be arithmetic. So you are going to be adding a common term to the previous term. So to find a sub 2, you will need the first term plus the difference. And we're going to go over this in a minute. So we have here example 1, and we have 3 different sequences. And so what we're going to do is we're going to go over how to find the difference. And so here we say, it says here, begin with when n equals 1. So that, of course, will be your first term, a sub 1. And that first term happens to be 7. So we're going to take the term that is after a sub 1, which is a sub 2. And that is equal to 11. And so to find the common difference, we are going to take a sub 2 minus a sub 1, and that will equal to 11 minus 7, which is equal to 4. Now let's try it with another 2 terms. So we are going to say 15 minus 11, and that will also give me 4. So far it's okay. Let's try one more time. So 19 minus 15 is also equal to 4. So from here, we could say that the common difference between consecutive terms is equal to 4. Now, to get the general term or the nth term, you could see here is an expression, an algebraic expression, and it will be 4n plus 3. So in the following examples, we're going to learn how to get to an expression like that. Let's look at sequence B. Now here we have that the nth term is equal to 7 minus 5n, and it is arithmetic. So for this sequence, the common difference is equal to 5. So let's see if this is true. You could see if they subtract the second term minus the first, it will be negative 3 minus 2, which is negative 5. Now let's try it with the third. So minus 8 minus negative 3. And of course, we got to be careful with those negative numbers. So this is going to be negative 8 plus 3. So it's going to equal to negative 5. So far it's the same as this one. And of course, we're not going to check the next one, but if you were to subtract negative 13 and then minus negative 8, you will also get the same. So sometimes sequences might have fractions, and we're going to treat them the exact same way, so don't be scared. It is the same thing. So in this case, the common difference could be 1/4. Oh, and also just going back to the second example of part B, the difference could be negative, like you see here, D is equal to negative 5, or the difference, of course, could be positive, like such as 4. And of course, we could also have a difference that is not an integer, so it could be a fraction. And in this case, we take the 5/4 minus 1. So if it is, if they don't have the same denominator, remember you have to find that common denominator. So 1, or negative 1, I should say, in terms of fourths is 4 over 4. So negative 4 over 4. And if we subtract that, then it will be 5 minus 4, now that they have the same denominator, and then we get 1/4. So if we were to check with our other fractions, you see the common difference will be that one at all times. However, the algebraic expression to find the nth term is n plus 3 and then divided by 4, or this is the exact same thing, 1/4 times n plus 3. They are equivalent expressions. So now we're going to go ahead and find the common difference for the sequence. And as you can see here, you have something that is not going to be arithmetic, but let's see why. And this is the sequence that represents the squares of natural numbers. So 1 square is 1, 2 squares is 4, 3 squares is 9, 4 squares is 16. So if we were to take the second term, 4 minus 1, you get a 3. Then if we take the third minus the second, we will have 9 minus 4, which is equal to 5. And if we continue with that pattern, and then we will see that we will not get the same difference. In fact, as soon as you get different values for D, after checking 2 of those differences, then you could say for sure that it's not an arithmetic sequence, because only one counterexample is enough to contradict the statement. So how do we find those D? And so, of course, you already know we're going to be subtracting them. So just to show you what I started to write on the second slide of the section, I wrote down that we find the second term by taking the first term and then adding that common difference, which is D. And so we get the second term. So as you can see on the following slide, if we want to get the third term, it would make sense that we say we will take the second term plus d. However, we already know that the second term, it happens to be the same as the expression that we have here. So it will be a sub 1 plus d. So I got that from here. But we cannot forget that we have an extra d here. And so if we combine like terms, we have d plus d, which will be equal to 2d. And that is what we have here. And that is another way that we could find the third term, because we know the common difference is the same. So then we're going to have, if we start with the first term, we will add the difference twice. And remember, when I say add, the difference could be negative. So in that case, you will be subtracting. So now going to the so now you know why it's a1 plus 2d. So if we look at a sub 4 could be equal to a sub 3, I should say, plus d by logic. But we already know that a sub 3 is equal to a sub 1 plus 2d, or actually we could just get that from here. So if I substitute a sub 3 with that expression, it will be a sub 1 plus 2d, but we still have d that needs to be added here. So plus d, so that will be equivalent to a sub 1 plus, combining those terms, we will get 3d. And so that is how we will find a sub 4. That will be equivalent to a sub 1 plus 3 times the common difference, which is d. So if we follow on that pattern, you can notice that when we have a subscript, in this case, the subscript is 4, and the times that we add the common difference is 3. So you can notice that it's going to be 1 less, because if you look at the previous examples, to find a sub 3, we added the common difference twice. So we have 2d. So you could see how it will be 1 less, the number of times that we add the common difference will be 1 less than the subscript. So for the fifth term, we will be adding the common difference 4 times, because it will be 5 minus 1. So we add the common difference 4 times. So if I was to find the sixth term, for example, a sub 6, it will be a sub 1 plus 5d, because 6 minus 1 is equal to 5. And so that is the number of times that we will be adding that common difference. Remember, 1 less than the subscript. So if we generalize that, 5 minus 1 or 6 minus 1 or 4 minus 1, 3 minus 1, depending on the subscript of the term, we could always say that it will be 1 less than the subscript. So in general, if the subscript is n, then we will use n minus 1. Just like we did with 6 minus 1, 5 minus 1, 3 minus 1, 4 minus 1, and all those terms. So at this point, with the help of this formula, then we don't have to find every single term before the nth term. So instead of finding, of course, you'll be given the first term. So instead of finding the second and then the third, and then the fourth, and then the fifth. And then let's say the question was to find the sixth term. So we will have to do all of that in the past, but now with the formula that we are learning from here, we're going to be able to just find any term. It could be the sixth term, or the question could even be, what is the thousandth term? And so we will be able, as long as we know the first term and the common difference, we will be able to find that term before, at once. I mean, not at once, but without finding all the terms before that particular term. So that same formula that we have written down here, it is summarized here. And I wanted to point out that every time you have a PowerPoint or a textbook, all those important things such as definitions, formulas, theorems, they can all be found in the inside boxes most of the time, or you can notice the title is bolded here. So those things are important, and they will continue to be important in calculus if you have to take it, or physics, or actually like any science class. So it's important to make note of that. And so remember to find any term on the sequence. That's what we use n to generalize the number. Then it will be the first term, of course, plus the common difference. And how many times? Well, that will depend on what n is equal to. So in this case, is n minus 1. Always one less than the subscript. So again, a sub 1 is the first term, and d is what we call the common difference. Okay, so on example 2, we're going to find a term, and in this case, we start with our formula. So when you do a formula sheet for this exam, please include this formula. It's very, very important. And that is to find the nth term. That's the name of an arithmetic sequence. Sometimes it's better to write a little explanation, not just the title or an example, but if you get used to that, just take advantage of it. It's better for you as a great way to study as well, to know what the formula is for. So the question says find a formula for the nth term. So remember how at the beginning we looked at some examples, and they were written kind of like, in fact, like linear functions. So I'm going to show you that slide here. 4n plus 3, or 7 minus 5n, or 1/4 times n plus 3. So that is what we're going to learn to find right now. So let's see. We start with the formula that we know. And so we know that the common difference is given to us here. Sometimes if it's not given to you, then you might have to find it. Like for example, if we just had like the sequence that you see down below, we would have taken 5 minus 2, and that will be 3, but they're already telling us here the difference is 3. Now remember, you should always check more than one difference. So 8 minus 5 is also 3, 11 minus 8 is also 3, 14 minus 11 is also 3. Okay, and I do have the answer here, but like don't pay attention to it, pretend it's not there. So we start with the common difference. We must have the first term, and that will be there. So you could see how the first term is substituted here with a 2, because that's what they equal. And then we have the common difference is a 3, so we have it there, d equals 3. And of course, we have n minus 1. So at this point, I'm going to simplify the expression by distributing the 3 to the n and the negative 1 by multiplying them. So 2, always start from left to right. 2 plus 3 times n is 3n. 3 times -1 is -3. And then we're going to simplify it by combining like terms now. So it's going to be 2 minus 3, so that will be equal to -1 plus 3n. And of course, we could reverse the operation, but keeping the same signs. So 3n minus 1, and that is actually what we have here. And they have the exact same meaning, -1 plus 3n or 3n minus 1. They're the same. So you could see here, if we were to plot this on the calculator, you will go to the section where you enter your functions like you do with, like you did in pre-cal, maybe linear functions, quadratic. Actually, we graphed some trigonometric functions in the previous chapters. And so you will enter the 3n minus 1, but if your calculator doesn't have the variable n, it's not a big deal. You could just use x, so 3x minus 1. You graph it, and then you should be able to see that. Now, some calculators do have a function where you will graph it as an actual sequence um, and not a function. And so the difference is that the domain for a linear function is all real numbers. So from -infinity to +infinity. And the domain for a sequence is the set of positive integers. Sometimes we include 0. So let's say n is greater than, in this case for this example, 1, and it is an integer, or we could say the natural numbers as well. So for that reason, when you graph a sequence, and I will show you during the lab session how to do that. And as you can see here, graphing a sequence, the line will not be solid as like when we graph a function. So when you graph a sequence, you will see the little dots if your calculator has the function. So that is the reason, because we don't consider the numbers in between 1 and 2. We just say the first term, the second term, and then we go to the third term. We don't worry about what is between 2 and 3. Okay, so that is how we found the formula for the nth term. And it's just by simplifying from the original formula, the one that we have here. So let's move on to the next example. So when you know the nth term of an arithmetic sequence and you know the common difference, so once you know the general form and you also know the common difference, you can find the next term, so the one that will be one after this one. So that's why we're calling it n plus 1, because these terms are consecutive, so it will be one after. And we could do that by using the recursion formula, just like we did at the beginning, or in fact in the last section. When to find the second term, it will be like a sub 1 plus d. Or to find the third term, it will be a sub 2 plus d. Or in this case, it will be, let's say this, a sub n, it will be like the term before it. So it was a to the subscript n minus 1, the one before, plus d. So if we want to find the n plus 1, the one before n plus 1 happens to be n. And so, that's if you have to find the nth plus 1 term, n plus 1 in parentheses, and then th to indicate the order in the sequence. So it will be simply the one after n. So with this formula, you can find any term of an arithmetic sequence provided that you know the preceding term, the one before, just like we can see on these examples, the one before. For instance, when you know the first term, you can find the second term, then knowing the second term, you can find the third, and so on, just like we did on this example here. Now, there is a formula to determine the sum or the addition of a finite arithmetic sequence. Remember, finite means that we know what the last term is. Even if your sequence is infinite, the question could say something like, find the sum of the first 10 terms, or find the sum of the first 20 terms, or so on. So only for finite. When we look at the next section, we're going to learn a formula to add finite and infinite, but of a different type of sequences. But let's not get into that yet. So in this formula, we have it here. And we have S to denote sum, addition. And we use the subscript N to denote how many terms are being added, like that. And so that N becomes very important within the formula, because we're going to use it here for the number of terms. And then we're also going to use the first term, as you already recognize. The subscript is A sub 1 for the first term. And we're also using the last term. So we're going to substitute 3 things to find that sum. But before we do an example, I want to show you, I cannot erase that now. Okay, so this formula was created or discovered, I don't know what to call it, by a guy that you might be already familiar with from matrix algebra. So the guy who was the inventor, creator, I don't know, or discover, or made the formula to do the Gauss elimination or Gaussian elimination. And his name, I believe, is Carl Friedrich Gauss. And so there's a story that says that he was in elementary school. He was a very smart kid, and the teacher was kind of tired of how smart he was, because he will finish all the work super quick. So she gave him a challenge to add all the numbers from 1 consecutive all the way to 100. And so she thought that he was going to take a while to perform that sum. And so he came up with this amazing formula. So let's see if you guys can follow how he figured it out. And I learned this from a professor, so I'm just sharing this with you because I think it's a pretty cool story. So he wrote down the numbers: 1 plus 2 plus 3 plus 4 plus 5, and so on, all the way to, let me write some more, 98 plus 99 plus 100. So then he wrote them again, but this time in reverse. So he started with 100, or in descending order, I should say, from the biggest to smallest. So 100 plus 99 plus 98 plus 97 plus, and then the last numbers were, the last one we know was a 1, so the second to last, or the preceding term, was 2, and the one before was 3. So then he thought about this: what if I add every column, if I add the numbers vertically? And so 1 plus 100 is 101. Then 2 plus 99 is equal to 101. 3 plus 98 is equal to 101. for 97 is 101. And you could see that for every pair of numbers, if you add them vertically, you will always get 101. Okay, so the question is, how many times does he have 101 being added here? And so the answer to that you could is the number of terms. So if it started with a 1 and ended with 100, he has 100 terms, or he had 100 terms. And so if he wrote the numbers, the sequence, or in this case, the series, twice, so he did that times 2. So then it means that he has 100 times 101. However, he doesn't need that 2 times. He only needs the addition of one of those. So for that reason, he divided by 2. And so what the formula happens to be, well, where the 101 comes from is from I'm going to adjust this. Well, it's going to be from 1 plus 100. And so that 100 happens to be the last term. You could see it here. And the 1 happens to be the first term right here. And that's what we have here on the formula. And the 100, it happens to be the number of terms that we had. And the 2 was just needed because he added the 2 series. Remember, when they're adding, they're called series. Twice. And so that's why it was divided by 2. So imagine, and I think he was in 4th grade. I could be wrong, of course. But imagine if a 4th grade comes up with something like that to you if you were a teacher. I mean, I would be a little jealous, but at the same time proud. So using that formula, now that you know where it came from, so we're always going to use the first term added to the last term, and then we're going to multiply it by the number of terms, but divide it by 2. And don't forget to divide by 2 because you only want to add the sequence one time, not twice. So we have a sequence here, and you could see it's, a series, but it's coming from adding the sequence for the odd integers, odd positive integers, we could call it that. So the first term, it is a 1, and the last term is a 19. And so that's what we need. We're going to need to know that a sub 1 is equal to 1, and we need to know that a sub n is equal to 19. In fact, instead of calling it a sub n, I should actually find what n is equal to. So to find what n is equal to, we need to count how many terms we have. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So n is equal to 10. It's not 19. 19 is the last term. So in fact, 10 is the little subscript for this term. So the 10th term happens to be 19. Okay, so now we're going to substitute into the formula. So of course, we need our last term, which we know is the 19, and it happens to be the 10th term. But with the place where we substitute the 10 is going to be here in the place of n, the number of terms. You can remember it that way. And also we have the first term here that we're going to substitute here. So let's get started. So we're going to have S. Remember, S is for the sum. And in this case, we're adding the number of terms, which is 10. The sum of the 10 terms for that sequence will be equal to 10 over 2. The 10 is n, times a sub 1, which is a 1, plus a sub n, which is a 19. So in this case, we need to follow the order of operations. And so that means that we're going to do what's inside the parentheses first. So the sum of the first 10 terms, or for this one, it will be, yeah, let's just do the parentheses for good practice. 1 plus 19 is 20. Okay, so now here we have a 20 divided by 1 because it's just an integer. So then S of the sub 10 is going to be, remember we have to multiply horizontally. So 10 times 20 is 2, and then with 2 zeros after, so 200. And then 2 times 1 is equal to 2. So then from here we need to reduce the fractions or simplify. So 200 divided by 2 is 100. And so that is what you will get if you add the 10 numbers that you see here. And so if you don't believe me, you can pause the video and check with your calculator. Okay, so we're going to move on to one of the examples for this section. Example 9, a small business sells $10,000 worth of skincare products during its first year. So that's going to be relevant. The owner of the business has set a goal of increasing annual sales by $7,500 each year for 9 years. So the owner wants to increase, meaning add, so the sales by that much each year. So every year he hopes the sales, if the first year they were 10,000, he hopes the second year they are 10,000 plus 7,500, so 17,500. And he plans to continue on that for each year for a total of 9 years. So assuming, and well, this is a little tricky because we're not going to assume that n is equal to 9. Instead, we have to say that we have to consider that we started with a sub 1, and that is 10,000. That was the first year. So if you consider 9 years after that, oh, and I did not write 10,000, right? So if we consider 9 years after 1, it's going to be n is equal to 10. And you could also see that on the question, but I guess I was just getting ahead. So assuming that this goal is met, find the total sales during the first 10 years. So again, that confirms that n is equal to 10. This business is in operation, so the first 10 years. Assuming that, the goal was met and that the sales increase by 7,500 every year. And because that number is constant, it's equal to D. Of course, in real life, it wouldn't be. But yes. And then what else do we need? We need the first term, which is A sub 1, which is 10,000. So you could see already here, and I'm just going to go ahead and write down the formula again below here. It's just a good practice. So we have the first term plus the difference, how many times? N minus 1. So as you could see here, A sub 1 substituted with 10,000, And then we have the difference substituted with 7,500. So at this point, we want to find the 10th term because I'm going to get a little ahead of ourselves. In fact, we're going to call this step 1. This will be the step 2 to find the actual sum, the addition of all the cells. So the question is not just what was the number, what was the amount of the cells for the 10th year. The question is find the total cells. So that tells me right there that I'm going to have to add the first year, second year, third year, and all the way to the 10th year. So because of that, for us to be able to use the sum for an arithmetic sequence, we need to know, and the formula is not here, so I'll write it here. We're going to need to know and actually I'll just write it in general terms, so that will be an n. So it will be n minus 2 times a sub 1 plus a sub n. So in other words, what we're looking for is a sub 10. That is the question. And you could see that the answer is already here. I just left it there so we can save some time with less calculations, but let's go ahead and find it. So we have a sub 1 it's already substituted. However, we're finding for the 10th term. Remember, that is the question right here. Pretend that we don't know what it is. So that's our question. First step, find the last term. So we're going to have 10,000, which is a sub 1. In fact, I'm just going to write the formula again. So a sub 1 plus d times, instead of n, we're going to say 9. I'm sorry, it will still be 10, but then we will subtract a 1. So you could see here how we are mm, we are finding. So if n is 10 right here, we're gonna find n minus 1, which will be 9. So now let's substitute everything. We're looking for a sub 10. A sub 1 is 10,000 plus d, which is 7,500. And then, of course, here is a 9. And I mean, you can substitute everything at once. I just wanted to make it very clear why the number that we use is 9. Remember, it's n sub minus n sub 1. So, okay, I'm going to pause this video for a second. Okay, so I realized what was going on. So it's actually, I'm gonna show you I'm gonna finish the way I started to find that term, and then I'm gonna show you the way that the PowerPoint had already written there so that you can learn both ways. So if I simplify this expression, the 10th term is gonna be 10,000, of course, plus the product of this 7,500 times 9, which is 67,500. And so if we add those two numbers, we will actually get what we were looking for, which is if we add these two numbers, we will get 77,500, which is the same answer that we have here. However, here it looks written a little different. So I'm going to show you how they got to that part. And so what they actually used was, let's see. So I'm going to need a little bit more room. So if you start with a formula like this, and it was, I believe it was the first term plus n minus 1 times d, and for convenience, they put the d at the front. So if we distribute D, we will get a sub 1 plus D times N, and then minus D times 1. And yeah, that's not really where I wanted to get with this. Actually, let's go ahead and substitute. So I believe they did something like this. The difference was already 7,500. And then we knew somehow that here we needed N, which is 10. Minus 1. So then S sub 10 was going to be A sub 1 plus this number times this one. Minus that. And so if we take 75,000 minus 7,500, 75,000 minus 7,500, and that gives us 67,500. Okay, and so you can see here they have the common difference plus this number. Yeah, I really don't like it. So I mean, if you feel comfortable doing that, that's fine. I don't know. Oh, I see how. Um, let's do the following. So S sub n will equal A sub 1 plus D times n minus 1. Okay, so I'm going to substitute everything that I know. The first term is 10,000. Then we have the difference, which is 7,500. And then we have n minus 1. So from here, we're going to take the 10,000 and then plus. Now I'm going to go ahead and multiply. So it's going to be 7,500 and then it's going to be 7,500 times negative 1. So it will be minus 7,500. Yes, that's what it is. So it's kind of like what was on the first slide or second, how to simplify the formula. So that's exactly what we're doing. So I just kept the n minus 1. That's what I'm doing. And then I replace this with D with the 7,500 and A sub 1 with the 10,000. So now I'm just simplifying the expression. So you could see that the two terms that are just constants, they could be combined. So in this case, it will be 10,000 minus 7,500, and that is equal to 2,500 or 2,500 plus 7,500 and of course I can reverse the order. 7,500 times n plus 2,500. So the way that they're showing here on the PowerPoint, that in the textbook, I assume that they found it is by using this expression, which is coming from what I showed you from the other slide, 7,500 times n plus 2,500. So that is the simplified expression from here. That's what they used. And so that's why you can see here the substitution is a 10. But if you were to use this form when you start, then you will still have to subtract 1, which this will turn into a 9. But as you can see, with either one, you will get the same result for the 10th term. So now let's move out to our second and final step. That will be how to find the sum, the addition of all those 10 terms. So we know that, and this is, I'm just going to make this correction. I've been writing S sub n, and that is so wrong. I should not write that because we're not adding yet. This was just to find the nth term. So please correct that on your notes. It's just bad notation, which can lead to a lot of confusion. So I apologize for that. I'm just trying to finish this video faster, but it doesn't matter what I do. I just talk too much. So let's go back up here. So the sum of the first 10 terms. So we're going to substitute n with a 10 and then divide by 2. We need the first term, which I believe was 10,000. And then we need the last term, which was 77,500. And so we substitute, that would simplify. 10 divided by 2 is a 5. And here we can add these two terms. So that's going to give us 87,500. And then we're going to have to multiply 5 times the 87,500. And we get 437,500. And you can also see the answer here at the bottom. So that is what the cells will be after 10 years. And so remember, you will need that formula to add the sequences. And then, of course, we also need the one that we have here. In fact, this one here, to find the nth term. But after you substitute, you could always find a variation or a simplified version, such as this one here. So that is also helpful to know. So thank you. This is the end of the video.